Okay, so dynamics. So one thing that I discovered, to my surprise, quite a few years ago, was that many of the standard tools and concepts and ideas that are used to understand dynamics on galactic scales, or even in very dense systems like globular clusters, seem to be not entirely relevant for understanding what happens near massive black holes. In many cases, close enough to the black hole, the system is collisional. That is, two-body interactions occur at a rate that is so high that, in fact, they dominate over the volume average potential that is supplied by the black hole and the stellar system around it. This is quite unlike the case in galaxies, which in most, I guess all cases, galaxies as a whole are collisionless. And even though the stellar distribution around the black hole peaks toward the center and the densities can become extremely high, many orders of magnitude higher than they are around the sun. For example, the mean density of stars around the sun is about 1/10 of a star per cubic parsec, and near the black hole it can in principle rise up to perhaps 10 to the 8 stars per parsec. Of course, the volume is tiny, so the actual number of stars that exist at such a high density can be only a few dozen or maybe 100 or most thousands. But these stars are exactly the stars that interest us. These are the stars that are most likely to interact with a black hole. Now, dense systems are known in nature. In fact, one of the most interesting systems to study from the dynamics point of view are globular clusters. The densities there, if they're very dense, can reach about, say, 10 to the 6 stars per cubic parsec. But these systems, as far as we know, do not contain a central object, a massive black hole. And therefore, many properties, like the fact that there is a mass sink in the center, the fact that the potential is dominated by a central object, are actually missing in globular clusters, and therefore the type of physics that we need to put in to understand them is different. And it turns out that, in fact, near massive black holes, because of the high degree of symmetry that the black hole introduces in the small volume where it completely dominates this potential, this high symmetry gives rise to all kinds of, let's call them in quotes, exotic phenomena. Coherent torques, phenomena otherwise known as resonant relaxation, which will be a key motif in this talk, and other effects, which I'll mention briefly as I go, are also quite new. They introduce new complication, new combinatorics to the old things that we thought we knew, and some unexpected results. Now, all of these are hidden in the inner parsec, or fractions of a parsec, 100th of a parsec in some cases, around the massive black hole, and we essentially have almost no opportunities to actually observe them directly. And this is quite different, I think, from the situation with the mergers of two roughly equal mass massive black holes, or what happens with galactic binaries. Now, I'm not trying to make you think that, or claim that it's easy to understand those processes, but at least we have some observational data to actually check our ideas against. We have very little direct opportunity to observe what's happening so close to a massive black hole, and there are only very few such systems, and because they're so rare and they give us an opportunity that we otherwise don't have, I'm going to focus quite strongly on them. So one, which I've been talking about for quite some time in other previous Astro-GR meetings, is our own Milky Way, for obvious reasons. It's very close. And another, where we have some information on what's happening close to a black hole, well inside its radius of influence, is provided by the maser disk of NGC 4258. And I'm going to spend some time telling you about things that I think we can learn from studying the behavior of that disk. Now, the consequences are manifold. Of course, we are mostly interested in this workshop to understand what all this means for EMRIs, but in fact it turns out that There are consequences also for the coalescence of massive black hole binaries, and maybe even for the actual evolution of what's happening here, of black holes themselves. So the process is in some sense iterative. So I started out by trying to understand better EMRI dynamics. Then the investigations reveal all kinds of new properties that force us to rethink what we know generally about the dynamics around massive black holes. This then has impact on things that are not directly related to EMRIs, but which are profound in our understanding of the system. And then when we learn more, we find that we can actually find more systems or more physical phenomena by which to check our ideas. This improves our understanding of its processes and feeds back on the EMRI problem. So this is a sort of a cycle which is, at this point, is not showing any sign of converging. And I'm not claiming that it's going to converge soon or that I understand everything. But what I want you to describe today are two stations along this cycle, recent results that we have obtained. And hopefully this is going to lead to ever more better understanding of what we need to know about EMRIs. And as I mentioned, the key point here is that it turns out that this exotic process of resonant relaxation is indeed key to understanding the dynamics of such systems. So, very briefly, the outline of my talk, I'll continue with this introduction, try and explain resonant relaxation. The idea, in principle, is simple. The implications can be quite complicated and unexpected. I will then discuss the recent result from a work led by David Merritt, where we uncovered a new dynamical mechanism which we call the Schwarzschild barrier, which actually prevents stars from becoming EMRIs or suppresses stars from becoming EMRIs. I will then go and discuss another implication of this relaxation with regards to accretion disks and what I think are the implications, general implications for the evolution of massive black holes over cosmic times. And then, time permitting, I will also remind you of some recent results about the resonant relaxation in our own galactic center. So, briefly, what is resonant relaxation? So, as I mentioned, if you have a system composed of a large number of discrete bodies, an n-body system, large n, it's unavoidable that over time, just by chance, a few of these bodies will interact rather closely, and then instead of moving in the time average mean potential of the system, they will experience sharp changes in their motion. And after, if you wait long enough, these changes, and they don't need to be very sharp, they just need to be substantially different from what they would do if they just followed the potential of the smear distribution. All these small perturbations add up, and the orbits are randomized. So this is the normal two-body or non-coherent relaxation, which is unavoidable since our system is composed of discrete masses and not of a smooth distribution. But on top of this, if your system has some special symmetries, for example, the system is dominated by the potential of a central mass, and at this point, let's just assume that this mass can be well approximated by Newtonian physics. So we know that each of the particles is, for a while, moving as if only the central dominating mass exists, and it's moving on ellipses which are fixed in space. This is the Keplerian ellipses. And therefore, over time, if you average the effect of one such star on another test star, the long-term effect would be as if you take and integrate the mass of the star, the background star, over its orbit, so you actually have a massed wire. You can think then of the entire population as an ensemble of massed wires, but a finite number of wires. There are only n stars, and n can be big, but it's finite. And therefore, at any given time, there will be fluctuations in the force that this ensemble of wires exerts on your test particle. The force will not average out completely because although the system is statistically speaking spherically symmetric, there are fluctuations due to the fact that it is composed of a finite number of stars, and 2, because it is because the ellipses are fixed in space, so they're not changing, and this force therefore is long-lasting. Now our test star will be affected by this in a way that its angular momentum will change. Its energy will not change at this level of approximation because the potential is fixed, so energy is conserved. But there will be a net force and therefore a net torque. And a star could, in principle, transition from somewhat eccentric orbit to a very eccentric orbit. And this will be a coherent effect that it will grow as a function of time, unlike the random scattering process where things grow slower as a function of the square root of time. And in principle, we are interested in these very eccentric orbits because these are exactly the orbits that will give us eventually EMRI. The periapse becomes small, the star will start emitting gravitational waves, the orbit will decay, and eventually it will decay to a certain period that both the frequency and power are high enough, the frequency is high enough, the power is high enough to be detected.
Tal, can you explain why this grows linearly in time rather than the square root of time?
Yes, because it's a constant torque, and J equals the torque times time. So, sorry, the angular momentum, the change in angular momentum, the accumulated change in angular momentum, delta J, grows as the torque times the time. Now, an analogous thing happens if you don't have a Kepler potential, but just a spherically symmetric potential. Your orbits will precess in a form rosettes, and over a long enough time you can smear out that rosette and think of it as an annulus of mass. So your background stars are a set of nested annuli at a random inclination. For reasons of symmetry, this thing cannot change the magnitude of the angular momentum of any single star, but it can change its direction, and therefore you take this kind of an orbit and you tilt it this way while conserving the shape of the orbit. And so, because here we change the magnitude, this is called scalar resonant relaxation, and here only the direction changes, it's called vector resonant relaxation. Now, let's put this in a more quantitative way. This is essentially the only slide with formula. They're really simple. Don't get too taken back by them. I will go through it. It's quite elementary. So, first of all, what is the residual torque on our test star, which is orbiting on some scale of, let's call that scale R, the size of the orbit. So any star exerts on it a force of gm star, a force per unit mass. So the acceleration is gm star over r squared. These forces add up in a non-coherent way. So the total force has a magnitude of square root of n times that, where n is the number of stars on that scale, and the lever arm times the lever arm, and I'm dropping here the angular dependence. This is just an order of magnitude estimate. The lever arm is r, so this is j dot, our torque. Now it's convenient to express the accumulated change in terms of some dimensionless quantity, and we choose to normalize everything by the circular angular momentum. That is the maximum angular momentum that the star can have on that scale. And I also introduced the shorthand notation of Q being just the mass ratio between the star, the black hole, and the single star. We are assuming that all stars at this point have the same mass, and P would be the radial period, or simply from Kepler's law, so I'm neglecting the contribution of the mass of the stars themselves. And when you write it down, you get this expression. So this is the accumulated change in the coherent torquing phase. Now, how long would this coherent time last? I mean, it doesn't last forever. The system is not strictly a Keplerian system. There are various other things that limit, that break the symmetry slowly, and will start making the orbits drift from their fixed Keplerian position, and therefore scramble the background that is torquing our test star. Now, just by reasons of self-consistency, since our choice of which star to consider the test star was completely arbitrary, all the stars are actually experiencing these coherent torques, and after some time, the coherent torques themselves will scramble the distribution of the orbits, and therefore there is some, and we call the self-quenching time. So basically, and this is just a sort of an order of magnitude estimate, once the accumulated change reaches an order unity value, let's just choose one for convenience, we know that this cannot go on. So this is the longest this thing can actually last, and if you just solve this equation by equating it to 1, you find the simple formula for the maximal length of time by which these coherent torques can act. However, it's many times the case that there are other faster quenching processes. For example, we have to include the mass of the stars in this story because it causes a small shift in the angle of periapse. And therefore, if you include that, you find that the actual maximum coherence time is given by this formula. And if you are close enough to the black hole where actually it's the GR Schwarzschild precession that dominates, then there is this dependence where J ISCO is the angular momentum on the innermost circular, stable circular orbit. Now finally, what will be the long-term result of having these finite coherent time, finite periods of coherence add up non-coherently? These are rather long periods of time. So you can ask yourself, let's suppose this is the thing that governs the coherence time, and this is the singular case where in fact the time to reach a order of unity change in angular momentum is in fact the self-quenching time. However, if it's the mass that is causing the precession, you get that this is the time for the orbits to completely forget their initial angular momentum. This is a much, much, much shorter than what you would get by two-body relaxation. Orders of magnitude shorter. And if it's GR, then you get this. So this was a primer on resonant relaxation. From here on, I'm simply going to show you results. Now you may wonder whether this is actually something that anyone sees. So actually, it actually turns out that it's extremely simple to reproduce resonant relaxation in any n-body simulation. It needn't be particularly accurate or contain many particles. You could see this effect if you know what to look for in simulations of a few dozen stars. But what I'm going to show you here are results from the state-of-the-art simulations that were developed by David Merritt using regularization techniques invented by Seppo Mikkola. And I'm going to show quite a few of these plots, so let's get used to them. This is a depiction of phase space. So this is 1 minus the eccentricity on a logarithmic scale. So here, where it's 1, the orbits are completely circular, and here, and going in that direction, they become progressively more linear-like. And this is the energy scale, or distance, as expressed by the semi-major axis of the orbits. Now these lines trace the change in these two parameters for a bunch of 50 stars during the course of one simulation where only Newtonian physics were included. Now, again, if the system was purely Keplerian, the points would remain where they were placed in the beginning of the simulation, since both the eccentricity and the semi-major axis are conserved quantities if you have pure Keplerian motion. But this is not a Keplerian system. It's an n-body system. It is not entirely dominated by the central point source, the central black hole. And therefore, the points are expected to change. But notice how remarkable the change is. They basically change almost entirely in angular momentum. The eccentricity at a given semi-major axis expresses the angular momentum. And you can see that there is a slight scatter on the vertical direction, on that vertical axis, which means that energy is also exchanged between the stars. But most of what they do is just zoom many times across. This is resonant relaxation in action, causing an extremely rapid change in angular momentum. And this line depicts the point where the orbits basically fall into the black hole. Yes?
Is this a 10 to the 6 solar mass central object?
It's a 10 to the 6 solar mass object with 50 solar mass black holes. The numbers are chosen because having a more realistic mass ratio would extend the time needed to for the simulation to run. But this is not a very, very far from, say, the parameters that express old LISA's targets or the galactic center. The surprise, another question?
What is special about this? Because you said it's just state-of-the-art.
Okay, this does not require state-of-the-art. The special thing is that SEPO's regularization method for dealing with extremely high accelerations, even at a few gravitational radiuses away from the black hole. I'm not I don't know to explain very well the details of that method. But however, the surprise was when we introduced all the post-Newtonian terms up to 2.5. So this includes the Schwarzschild precession. This is a non-spinning black hole. Spin will not matter much for these types of investigations. And it includes also gravitational wave emission. The idea was to try and reproduce an EMRI. And what we found was that there was this barrier where stars indeed scatter a lot back and forth, but they almost never seem to cross this barrier. And this was discovered first in the simulation. We did not anticipate it, at least not entirely. We already knew, Clovis Oppmann and I made the hypothesis that resonant relaxation will be quenched when the star approaches an orbit that is already close to emitting gravitational waves, and we were hoping that it would actually stop the stars from dropping all the way into the black hole. So nature will be benevolent, and the fact that the GR precession quenches the resonant relaxation torquing would actually work for enhancing the rate of EMRIs, but we did not expect that it will work so good that it will actually prevent them from getting there at all. Now, you do get a few EMRIs at a rate which is much lower than you would anticipate. This is, as far as I know, the first ever realization of an EMRI in an n-body simulation that is completely self-consistent, up to the fact that it's only a perturbative GR that is used. So you can see that most of the stars are locked above this red dotted line. I will explain later where this comes from. But every now and then, a star manages to break through the barrier, and here it's just scattering back and forth, also scattering quite a bit by combination of energy relaxation and gravitational wave emission, until it crosses the blue line, which demarcates the point where the energy losses from gravitational wave emission occur on a much faster rate that the star can be scattered back and forth to orbits that have a larger periapse and therefore are not emitting efficiently. So basically this is the point where GR wins over scattering, and then the EMRI executes the predicted, on this kind of a plot, the linear trajectory, which leads it at finally crossing the event horizon and merging with the central black hole. So this is the first realization of such a thing in an n-body system.
So then you are starting there with 50, what is it, 50 stars? No,
it's a very small system. It's 50 stars. As I mentioned, the black hole of 10^6 is stellar mass of 50, and this is the...
And they're between 1 milliparsec initially and...
Yes, they started at 10, I think it was, what is it here? I don't remember exactly the outer. I think maybe 50, I think, started out. This is an escaper. Okay. So, one thing that we already had some clues about that back in Paris last year, but now I think we know to explain it better, is what is the origin of that Schwarzschild barrier. And a simple way, this can be derived in a somewhat more formal way, but I'm giving you the easier to explain and more intuitive version. So this is, here I'm assuming a two-dimensional system, so everything is in the plane. And I'm simply going to write down the equations of motion for a star that is precessing under the influence of GR Schwarzschild precession, and at the same time is subject to a specially uniform force field, which is an approximation for the effect of the perturbation, this Poisson perturbation. Now that's actually a rather strong assumption, and it works very well for reasons that we don't entirely understand. But as I said, we also have the somewhat more formal derivation, at least, that drops the assumption of 2D and actually solves this straight out of from a Hamiltonian formulation. So this is not completely hand-waving, but there is this piece of approximating the effect of the Poisson perturbation as a fixed force field, which is sort of counterintuitive. So, but anyway, let's just take it as given. So, since the semi-major axis is not changing, neither the GR precession or the resonant relaxation torques affect the energy of the orbit. The semi-major axis is fixed, and there are two variables in the plane are the eccentricity of the orbit and the angle of periapse. And you write down the equations of motion. So an elegant way of doing it is to define everything in the dimensionless quantities. So we introduce little j to be simply the normalized angular momentum, which is essentially an alias for the eccentricity. We will normalize time by the self-quenching time, since the self-quenching time is the time it takes the system to rearrange itself again. So the force by the perturbation after one relaxation to self-quenching time has a completely random direction. And this parameter alpha basically quantifies how relativistic the system is. So this is the ratio between the mass of the black hole and the mass in the stars, and this is the ratio between the gravitational radius of the black hole and the size of the orbit. So the bigger A, the more relativistic the orbit is. And with these, the equations of motion are very simple. I won't derive it, but it's easy to show that the change in the angular momentum due to the torquing by the fixed force is simply given by this, and it's angle dependent because the force has a particular direction, and as the orbit precesses, the force sometimes torques it in one way, and once it precesses by pi, it torques it the other way. So it fluctuates and between maximal in one way and maximal the other way. And the first order Schwarzschild precession formula in these normalized units is simply given by this, and obviously the more relativistic the orbit, the faster the precession rate. Now, the Schwarzschild barrier turns out can be derived simply by requiring that GR will become as fast or faster than the rate at which the resonant relaxation torques operate. So basically, once GR wins over, the orbit precesses so quickly that the torquing cancels out and goes away. And this can be written up to some factors of order unity by requiring that the relative change in angles is the rate of relative change in the angle is equal to the rate of change in angular momentum. And when you solve this, and it's trivial algebra, you get that red line that we saw on the other plots, which demarcates the Schwarzschild barrier. Now, if you actually look close up at such an encounter, so the star, as we saw, moves from the right to the left and then bounces at the barrier and goes back. When you look closely what happens, you see that there is a period where the star is locked in some oscillatory behavior. So here we have the semi-major axis, which in principle shouldn't change, but it is changing slightly because it's not just GR and resonant relaxation, but also normal relaxation is still operating there. So but the change is rather small. Let's ignore that for a minute. We can look at the angle of periapse. This is telling us that there were maybe something like 1, 2, 3, 4, 5, 6, or 7 GR precession periods occurring during that encounter of the star with the barrier. And at the same time, the eccentricity also goes oscillations. And when you use that Hamiltonian model that we developed, and I don't have time to go into details, you see that it actually reproduces these generic results very well. We've seen many, many examples of such behavior near the barrier, and they can be explained quite straightforward from the properties of the solutions of those two coupled differential equations, simple differential equations that I showed you. So we believe that we have now only one assumption that we feel uncomfortable with, and that is that of the fixed force. Apart from that, I think we have a very good, at least approximate solution to explain why this barrier exists and what is the meaning of the behavior near the barrier. Now, this barrier is not completely waterproof. Stars can go through it, and the way it happens is actually shown very nicely in this plot. So here is a overplotted 4 or 5 cases where EMRIs actually stars managed to cross the barrier to become EMRIs. And it shows their trajectories in phase space from the time that they cross the barrier. And what you can see is that they execute some random walk here, and that cross the point where gravitational wave dissipation becomes faster than the scattering and become EMRIs. In this region, what is operating on them is the old normal two-body relaxation. And you see that it so happens that the distance that you need to cross in order to make the jump from this point to the point where you're in EMRI actually increases the closer you are to the black hole. So you need to make the horizontal jump in angular momentum from a very circular orbit to a very eccentric orbit, and this you can do if you're lucky enough to get scattered by two-body encounters in just the right way, but the gap is becoming progressively larger as you're closer to the black hole. And in fact, this means that if you're too close to the black hole, say you're just around here, the chances of that happening over a coherence time is essentially 0. So an orbit which is very close to the black hole is actually protected from the effects of resonant relaxation, and the star can linger in that orbit, even though it's much closer to the black hole than its friends up here, which actually can find themselves getting kicked into an EMRI orbit and falling into the black hole. And this is just one case. You can the size, the region where you can get past the barrier with the help of normal two-body relaxation is given here by this red line. For one example, the shape of these plots is always rather similar, but the exact position of the region where EMRIs are allowed changes with your assumption about the slope of the cusp, the number of stars there, and their masses, and so on. But this is a generic form. And stars that lie in this triangle here, so in this case, stars that are closer than, something like 15 or something like that, milliparsec, are basically protected from resonant relaxation. Now, this means, and by the way, stars that initially find themselves here have no problem to wander and become EMRIs, but that would be something that will happen only a short while after the system is formed. Once these stars are evacuated from their area, all other stars have to come from larger distances, so they have to cross somehow like this, and they will get blocked here and will simply stay here for much longer times that are commensurate with the two-body relaxation. So the net effect on the EMRI rate, by the way, is that it is suppressed by a factor of 10 to or 100 even. 100 is a bit exaggerated. Let's say this range is a typical number is closer to 10. They're suppressed by a factor of 10 over what you would expect if you were ignorant of this process. But the good side here, maybe for observations of the galactic center that Stefan will be speaking later, is that in fact you have reasons to be optimistic of finding stars very close to the black hole in that protected region. Okay, so time is running very late. I will try at least to talk about so that was that. That's one immediate implication of residual relaxation from EMRI rates. But now we want to discuss a very recent result. It's a paper we work on with my graduate student, Michal Bregman, which will be submitted very soon. And it has to do with the effects of resonant relaxation on the behavior of disks that feed black holes, and through the fact that it alters the properties of the disk, this will actually may have quite significant implications to the way that black holes grow, both in mass and in spin over cosmic times. So the departure point here is that, as I said, there are only a handful of accretion disks that we actually can image. And a very special class of circumnuclear accretion disks that can be imaged are those that are emitting in radio maser. And then because of the very high spatial resolution of large baseline interferometry in the radio, you can actually resolve these disks. So this is the most famous case, the first discovered and the cleanest case of a nearly Keplerian maser disk, which is fitting an AGN in the galaxy 4258. It's, what was it, 8 megaparsecs away? I don't remember exactly. And this is a composite of a model and the observation. This is the radio image of the central engine. The red and blue dots are points of maser emission observed in the radio, and they are fitted by a dynamical model for a disk, which turns out to have a warp of about 8 degrees on the scale from the tip of the basing region to the outer to the inner tip, which when translated, 7.2 megaparsec, when translated to physical distances, this lies between 0.14 and 0.28 parsecs. This is a massive black hole. It's about 10 times as massive as the one in our galaxy, and its radius of dynamical influence extends up to 7 parsecs. So this is a very small fraction of the volume affected by the dynamics of the black hole. Now, one slide primer on properties of disks. So this is a cut through a disk, through a warp disk. And this disk has, this R is the radial distance from the black hole. In this case, it's shown to be rotating, but this is not going to play a role just right now. Or maybe let me mention that if the black hole is spinning, then there is frame dragging will tend to warp, to align the inner parts of the disk to the plane of rotation through a mechanism called the Berdin-Peterson mechanism. But right now, let's ignore that extra complication. And the disk also has a vertical structure where is a function of the height. And typically, the disk is hot and has high pressure in the center, and it becomes cooler and with lower pressure as you go up. And that's depicted by the yellow and blue regions. Now, there are two types of viscosities going on at any given time if the disk is warped. One only if the disk is flat. So in any disk, flat or warped, you have a gradient in the velocities because the disk is almost Keplerian, and therefore the velocities are fall down as roughly the square root of r as you go further away from the disk. This means that let's just imagine conceptually that we can divide this disk into these two blocks with a well-defined separation. So along this line, you have this gas moving faster than this gas, and therefore they shear against each other. This shear causes viscous torques. The source of the torques is not like torques that we have here in high densities on Earth, where gas or solids or liquids actually have molecular friction. The gas is too rare to have that. These torques are probably mediated by magnetic fields, and it's a big field of study in itself how exactly this occurs, but we don't need to know the details. We know that we simply have to assume that such a torque exists, and it's proportional to the pressure that these two slabs exert against themselves. Now, when the disk is warped, there's also a pressure gradient as a function of height. And again, looking at this conceptually, we see that what happens is that in this point, the hot gas in the center is pushing against the colder gas in the rim of the bent part. Yeah, I know. And the direction of the pressure is opposite in this side. And therefore, you can imagine that if you push it in these two opposite directions, what happens will be that part will simply tilt downwards. And therefore, the disk will want to align itself on a diagonal, but as a flat disk. So these two viscosities may be actually related to different physical mechanisms, but there are all kinds of simplified models that tell you that when one is large, the other is small, and vice versa. So we will simply adopt these prescriptions. And now, what we do, we take the actual differential equations that govern the behavior of a disk under its own internal torques, both the horizontal that makes the gas flow in and angular momentum flow out, and the vertical one that straightens disks that are warped. We add to that the Berdin-Peterson torque from the central object, And we also add some highly simplified realization of the torque from a fluctuating background of millions of stars. Of course, that we cannot simulate directly, so we use some simplified form. I won't go into details. And what you get is that you then evolve in time the system, and what we have here is a model 44258, and you can see that the amazing region is highlighted in blue, and this, if you look at the cut through this, what it looks like over time is something. This is slow. Hold on. It's not only slow, it's dead. No, it's also black on my screen, which is sort of reassuring. I haven't. Okay. This is I guess it's not working. I'm probably out of RAM or something. Okay. Just kill this. Just imagine this flipping back and forth with many different vibrational modes over time, okay? Anyway, we're running out of time. So what do you actually see when you measure this quantitatively? So, first of all, this is the warp angle here as function of time for different assumptions about the initial conditions that the disk finds itself relative to the spin of the black hole, and sometimes with the Bardeen-Peterson switched on, sometimes with assuming that the black hole is Kerr. And look at the wiggly parts. You can see that over time, the region between 0.14 and 0.28 parsecs, where the maser is actually seen to be emitted from, cross the observed 8-degree line. And if you look at the statistics, I don't know if you can read it, they're between 1/4 or 0.4 of the time above that limit, which means that if this is the mechanism that explains the warping in the observed maser warp, then it's a very reasonable mechanism because it can produce such a warp for order unity of the time in the disk. For a particular choice of the angle between the spin of the black hole and the disk, the Bardeen-Peterson warping never actually reaches 8%. In fact, it is possible if you choose the alignment just right to explain this barely by the Bardeen-Peterson effect, but that requires a very high degree of fine-tuning. This does not require any fine-tuning. It just happens because stars exist around the disk. An other interesting fact is that because you add more viscosity when you warp the disk, the matter flows faster because you're basically when the disk the force that the disk has to exert to straighten the disk back to a flat alignment has to come from somewhere. It comes from the orbital energy of the inflowing gas, and therefore it flows inward faster. You get lots of spikes in the accretion. The overall enhancement could be of order of 1.5. At any individual event can be even 5 times as high as the mean. If you look at if you do a timescale analysis, you can see here that this variability is intimately tied to the warp. So the red is the warp, the blue are the long period fluctuations. You can see by eye that the two are correlated. The warps are causing the change in the mass accretion rate, and you can even with some analysis, come up with a rough formula to predict the type of the variability. It's long. For 4258, it's 10 to the 7 years. This is not the small-scale variability that we see in quasars. That's it, as far as I can tell, because my model for the fluctuation spectrum is crude. Maybe there are stars very close to the center that actually contribute something even on shorter timescales, but that's speculative now. Another thing that we see is that the covering factor, because now the disk is not planar, the covering factor of the disk relative to the central source in the center is rather large. It fluctuates between, say, 0.1 and 0.3, which means that the disk is intercepting the ionizing continuum from the center, and this actually is in almost all models of emission of accretion disks, active and active nuclear accretion disk, is assumed ad hoc to explain the properties of the disk. So this is telling us that resonant relaxation warping actually provides this for free, or it's almost unavoidable that the disk will be exposed to the central continuum. And finally, and I don't think I'm going to get to the galactic center stuff, so let me just mention that this also, through the Bardeen-Peterson effect, introduces a jitter to the direction of the spin. So this is a model for a massive AGN-like disk. It's not related to the model of 4258. And over 1 salpeter time, you can get, which is the time it takes for the disk to gain mass by a factor of E. You can, the pale blue line are the scatter in the direction of the normal to the disk, and the red and the purple line is the resulting scatter in the direction of the spin.
Central black hole?
Of the central black hole. It's not allowed. In the very limited set of models that I tried to simulate at this point, I did not do a full parameter survey. It's numerically quite expensive. In the amplitude of the scatter is of a few degrees. From what I heard from colleagues who are more knowledgeable than I am about jets, the width of jets is also from tip to the point where they interact strongly with the intergalactic medium is also a few degrees. So in principle, this could be there could be actually opportunities to constrain this model against the actual width of observed jets if you assume that the jets trace the direction of the spin. This is just I'm just now giving you my thoughts about things that can be done, and I'm essentially over my time, so I'll stop here, and if you want to know about the galactic center, come ask me later. Thank you.